Hello, everybody. Hope you're doing well. In this present lecture, we will discuss the asymmetric potential well, which is a very simple problem in quantum mechanics. It is confined to a one-dimensional problem in space. We will consider just one dimension, but it highlights some key features when solving bound state problems, especially when you have an abrupt transition in the potential, and you need to match wave functions in distinct regions of the problem. It is a more simplistic problem than the symmetric well with finite potential. In this case, we have infinite here, we have infinite in this side. For negative values of x, the potential is infinite, but from 0 to some distance, which is the size of your potential well, you have 0 potential energy, and b after this value here, the potential assumes a value u0, and this is bigger than larger than 0. It's a positive number, but it's less than infinity at this side. All right, so this value is a finite number, right? And it can be promptly related to a two-level problem and to tunneling, as we will see when calculating these things here. All right, so the problem is to solve this potential. We have the region 1, we have the region 2. There are two regions, and at x equals to d, we need to match the wave function. All right, this is the main problem here. All right, let me erase something I wrote previously here. So our problem is the following. We have an Hamiltonian. The Hamiltonian is one-dimensional, right? So momentum operator squared divided by twice the mass of the particle. This has only one component, which is related to the x-axis, plus that potential profile at the right-hand side of our board here. All right. So, as a matter of fact, we are wanting to solve the time-independent Schrödinger equation, which corresponds to an eigenvalue problem, right? So we are trying to find out these cats, and when projected to the position basis, when represented into the position basis, we have this thing here as previously. All right, I am doing the whole procedure because it will help you to remember what steps are needed, or what you need to do. But this way, this Hamiltonian, when p sub x is represented in the position basis, we already know it is minus I h bar, the derivative with respect to x, the x variable. I can put the total derivative or a partial derivative if you have more dimensions. In this case, we are considering time independent, so this is a total derivative, and we can plug in the d for total derivatives. All right. So in this case, this is the wave function psi of x. Notice that we are not worried about time here. It's time independent equation, so it's an eigenvalue problem, and we will have minus when squared, that operator, minus h bar squared divided by twice the mass, second derivative, because it's the square of that operator. It acts on the wave function psi of x plus the potential, which acts also on psi of x, and this is to be equal to the eigenvalue of the problem psi of x. All right, so there are two distinct regions. Wave function, we already know here the potential is going to infinite at the left hand side of the x-axis. All right, so in this region here, in this third region, the wave function is exactly equal to zero, so it must start being zero at this point, which is the same problem when dealing with two infinite walls. All right, but in this case we have infinite wall only in this side of the potential. In the other side, on the other side, potential is finite. All right, this is what we are trying to solve right here, right? So this is a differential equation. There are two regions for this differential equation. So we already know that x lower than zero or equal to zero, because the potential starts right here, the function is zero, so we do not have to worry about negative values of x at this point. All right, and we have two regions. So region one for the potential, the equation is equal to the following differential equation. All right, so this is the function at the region one. Let me call it the psi one function. All right, I'm writing this Roman numeral or number here. Okay, and of course the potential in this region is zero. In this region, which stands from 0 to d. All right, in this region potential is 0. And in the second region, region 2, the potential goes to u0. So the equation can be written the following way. Which is a constant, of course. So this just, I can move it to the right-hand side of the equation. It just subtracts from the energy of the particle, right? They are function of, they are functions of x, of course. They are functions of position. And we are interested in bound states. Bound states corresponds to the following. Psi of modulus of x going to infinity, it must go to 0. For negative x, we already have that accomplished. But also for bound states, we want the bound states are particles confined inside the well. All right, inside the well, the energies must be lower than u naught or u0. Right, the energies must be below the top of the well. Right, so in this case, particles will be confined inside the well. This is a simple problem, but it highlights a feature, which is in solving the eigenvalue problem, we will get a transcendental equation which has not prompt solutions. You need to solve it numerically. All right. Well, in region one, this is a very well-known differential equation. We can solve this by two exponentials, one moving wave to the right and one moving wave to the left, but they interact, or they interfere, to be precise. And in the same manner as we discussed for the infinite potential well, it can be just written as trigonometric functions. So some a constant, I'll call it a sine of kx, plus some a prime, some another a1, say some another constant, the cosine function of kx, where here, where this k must be the square root of 2 times mass times the energy, which is the eigenvalue we want to solve. All right, so k is related to that eigenvalue, or the energy eigenvalue is related to the k, the moment, pseudo momentum eigenvalue, if you multiply it by h bar here. All right, and for region 2, we must remember that this potential is higher than the eigenvalues we want to solve, we want to find, and we can eliminate this minus sign here if we just move this u naught to the right hand side and reverse the difference. All right, so the equation here, you can write it the following way. Okay, just move the u0 to the right hand side, so you'll find plus e minus u0, but you can change sign of the equation, so you have u0 minus e, and this solution here in the second region, remember that the second region is unbounded, so that u0 potential goes to infinity, and there is no room for a reflected wave. We are talking about evanescent waves. Of course, you could have a growing exponential, but it would lead to a value for the function tending to infinity at x going to infinity. So you need to eliminate that part of the solution, and you have some b, some constant to be determined, exponential of minus alpha x. All right, you could have some b1 exponential of alpha x, but this b1 must be zero. Otherwise, your solution will diverge at infinity. So we neglect, we eliminate that part. All right, and of course, alpha. If you plug in the solution here, you'll find out what is alpha. Alpha corresponds to twice the square root of twice the mass, u0 minus the energy eigenvalue divided by the h bar squared. All right. So notice that you could write this alpha as 2 times u naught divided by the h squared, all right, minus twice the mass times e divided by the h squared is just the k squared minus k squared. Notice that alpha and k are related to each other, all right? Well, remember that the wave function, which is in the region 1, psi1 of x equal to 0 must be 0. It must vanish there, because the wave function for x values lower than 0, or negative values of x, must be 0. You cannot have any probability of finding the particle in a region where the wall is perfectly rigid, or the potential goes to infinity, which corresponds to that part here of the potential. All right, potential has this profile. So to the left side, the wave function is 0, starting at x equal to 0. And if you consider this into the more general solution, you'll find out that sine of k times 0 is sine of 0. The sine of 0 is 0. No problem with that part. But the cosine of 0 is 1. So you are left with only one alternative. So A1 must be 0. This is because of this condition here. Your wave function here, no matter what is the solution here, must be 0 at x equal to 0. You don't know what happens after. Well, you already will know because it's a sine of kx, but right at this point, function must be 0, and that part of the solution never will be 0 unless your constant a1 is 0. All right. Therefore, the solutions we are talking about have the following properties. Region 1 corresponds to 0 lower than x, which is lower than d, or at least equal. This is the region 1, right? In this region 1, wave function is a sine of kx, and in region 2, all right, in region 2, which extends from x greater than d, or at least equal to d, we need to match the wave function. So in this case, we will have to have this function equal to that. So it's not a problem to put the equality sign both regions, all right? But if you want to be very precise, perhaps x greater than 0 in this region here. Well, I will leave the equality sign also. In this region, the solution is an exponential, all right? Minus alpha times x, all right? Well, we already know k is equal to that parameter, which depends on the energy. And alpha also depends on the energy. The potential parameter will be defined. It's a priori value. You already know that, right? So k and alpha we already know. This wave function is already 0 at x equal to 0, and we need some boundary condition. So some continuity conditions at the interface of region 1 and region 2, which is x exactly equal to d. This is the interface between these two distinct regions. We have to have the continuity of psi and the derivative. Why is that? Because probability must be conserved. And this is somehow related to some current, and current also must be conserved. All right, I'll not discuss it further, but this is what is required at x equal to d. And this way, we have a sine of k times d, which is the function at region 1, must be equal to the function at region 2. So b exponential of minus alpha times d, which is the size of the well, right? And for region 2, or sorry, for the derivative, when you just calculate the derivative here, you'll find out k times a times the cosine function of kx, but you must evaluate at x equal to d. So this is the derivative. So this is wave function here. So condition 1, condition A, say, and this is B. Right? From A, you'll get this equation. From B, you'll get the derivative. So the derivative of this function is minus alpha b, the exponential, and the exponential must be evaluated at x equal to b. So minus alpha b exponential of minus alpha d. All right, this is what you have. But now you can redefine the constant b. So in region 2, you could redefine b as some b prime, which is b e to the minus alpha d. Notice that alpha depends on the eigenvalue, but b will also depend, and this appears in both equations. So we can redefine the b as some another constant, say b prime equals to b times e minus alpha d. And this way, if you redefine that, you'll have in replacement of b, you can put b prime, and b prime will be or b will be b prime times the exponential of alpha d, and you'll find out minus alpha x minus d. All right, so this is a possible solution. You already inserted the fact that the solution starts at x equal to d. All right, and this b prime value here is just the value at x equals to d, which must be exactly equal to a sine of k times d, right? But just a aesthetical matter. It's not relevant to be honest. Well, in this case, we can rewrite these equations in the following way: in a matrix form. These two equations in a matrix form. So we will have sine of k times d, and if we move this factor to the left hand side, we will have minus 1, because I am replacing this for b prime, right? Do not be confused with derivative. It's just another constant, all right? So it's just a constant, right? So if we move to the left, it will be minus 1, and this here will be k, the cosine of kd, and this will correspond to alpha when we move to the left hand side of the equation, times a and b primed equal to 0, 0. This form of the equations in matrix form, in matrix notation, admits only one way of solving the problem, which is the determinant of the matrix is equal to 0. All right, this is the only way you can solve that equation. In this way, you will find calculating the determinant alpha sine of kd is equal to or plus k, the the cosine function of KD is equal to 0, which means your solution can be rewritten in terms of the energy eigenvalues. All right, so we'll find out. You can just move that some terms to the right and some terms to the left. So we'll have alpha function, which is the square root of 2 times mass times the u naught minus the energy divided by the h bar squared. All right, this is alpha, must be equal to minus k, which is square root 2 times the energy divided by h bar squared. Right, this is k. The cosine, this is k. I will write k. Right, cosine divided by the sine function. We can divide all the things by sine. So if you move it to the right, you get the minus sign. This is k. Cosine divided by sine is the cotangent function of kd. Right? So your equation can be written this way. Alpha is equal to minus k cotangent function of kb, where alpha is that and k is that. Right? This is your eigenvalue equation. Only the energies which satisfy this equation will be a solution. All right? And how can you solve that? Well, the possibility is to solve it numerically. The only possibility. All right? In this way, of course, if you have the solution, let me erase here, you'll find out that from this equation, sine of kb times a is equal to b prime. So b prime is already defined from your eigenvalue problem. This is an eigenvalue problem, but notice that this equation have, for unbounded states perhaps, an infinite number of solutions. All right, so but you need to replace the alpha here by some complex number, some imaginary number, purely imaginary number, but your equation here has an infinite number of solutions. But when you are considering bounded states, for bounded states, this will lead to a finite number of solutions. All right? How can you implement that in a computer? Of course, you can solve the problem numerically in a computer. Use the previous lectures to solve it numerically. You just discretize the Hamiltonian, you define the potential and solve the problem. Okay, you'll find out the solutions, but the other way is analytic, and in analytic situation you will be led to this equation here, which is an eigenvalue problem, and this equation, which will allow you to find out the values of the energy, is a transcendental equation. Okay, because if you expand this thing here in power series of kd, it will lead to an infinite number of terms depending on k. All right, and therefore you need to evaluate this by graphical methods or numerical methods or whatever. You can do that. Well, let us take a look at the alpha solution here, the alpha parameter. In order to solve that, you can just sweep values of E. In this case, you are trying only bounded states. You are concerned with bounded states. So the values of E from 0 to U0, this is the range. You plug in here, the mass of the particle is a constant already known. H bar is Planck's constant. U naught is just a parameter of the potential profile, right? So what you can, the D, which is the size of your well, is also a parameter, an input. So what you can do, you plug in values of E here, calculate the alpha, calculate the K for that E value, and look that look for a value of E which solves this equation. So if alpha is equal to that, that's a solution of your equation. And a graphical, you can make a plot in a computer, all right? A graphical representation will be the following. Because remember, alpha is equal to some constant, u naught minus E. You can plot the functions. The other function is, say, this is the function 1, and your function 2 is minus k, the cotangent function of k times d, and k is the square root of 2 times mass times the energy divided by h squared. You can plot functions f1, f2 as functions of energy. But remember, at the energy equals to 0, you have the upper limit of alpha in this range, which corresponds exactly to square root of 2 times mass times u naught divided by the h squared. And this is a square root which goes to 0 here when the energy is equal to u naught. All right, this is what happens. And for the other function, so this is f1, f1. Right, this is f1. If you plot the function f2, it is related to a cotangent multiplied by minus k. All right, and this function goes like this. It is periodic. You must take care because in the computer, perhaps the computer connects the dots here at the discontinuities. And discontinuities of this function occur anytime k times d is equal to a multiple of pi, because this is a cosine function divided by a sine function, and the sine function goes to 0 at multiples of pi, and in this way the cotangent goes to infinity, plus or minus infinity, depending on what position. So at the discontinuities you have non-solutions, but in your computer perhaps it is connected. This value is connected to the other one, and you will find a straight line and a vertical line. So do not be confused. You must be sure that these lines are discontinuities. So this is a function f2, all right? In red here is function f2, and each time your functions, your curves cross each other, are equal, you have a solution. This is a solution. This is a solution. This is a solution. So in my example here, you have three energy eigenvalues bounded inside the well. All right, so in this example, you'll find out three solutions here, here, and here. And the corresponding value you'll find out in the horizontal axis of this graphical method. All right, so this is a graphical method. Of course, a graphical method has an intrinsic error because you're just looking at your graph. Oh, it's equal at that point, but the uncertainties here is due to your eyes looking at something which is not it's a graphical, right? So you depend on the precision of your eyes, right? But of course, you can tabulate, you can make a table of energies, values of F1, values of F2, and find out where they are nearly equal or equal. Numerically, equality perhaps is, aside from special situations, is not exactly possible. But you can tolerate some errors. And in this region, in the neighborhood of this region, you know that there is an eigenvalue for the problem. In the neighborhood of this region, there is an eigenvalue. In the neighborhood of this region, there is an eigenvalue, which solves your transcendental eigenvalue problem. All right. So in my example here, in my arbitrary graph I did it here, you'll find out three solutions. All right. But notice, because alpha has this characteristic, this feature of going to lower values as the energy increases, it is natural because when you are near the top of your well, the particle has almost the energy necessary to go outside. So the probability of finding the particle outside the well becomes larger, and alpha parameterizes the probability of finding the particle outside the potential well. And in this case, notice that the higher level, the higher energy of your solution, most extended to outside the well, to outside the box, your particle will be. The probability of finding the particle outside the box increases. It is evanescent, it is exponentially attenuated, but it increases for higher levels. And when you extend that lines of reasoning to a three-dimensional atom where electrons are bounded to a potential well, of course, the higher energy levels, which corresponds to the larger numbers, principal quantum numbers, of course, the orbitals are more extended, which means the probabilities of finding the particle at larger distances from the nucleus, from the ion, at the center of your system, becomes larger. And therefore, valence orbitals, which corresponds to the highest quantum numbers, the occupied quantum numbers of that atom, will interact more with another atoms in the neighborhood, because those orbitals, the higher energy levels, will be more extended. All right. This is a very particular situation here because you are dealing with one dimension, you are dealing with abrupt changes in the potential. For atoms, the Coulomb potential is not abrupt. It's not, it does not vary in an in an abrupt scenario, but the main features you can borrow from this simple problem. All right, for higher energy levels, bounded states are more extended over space. There is a lesson which is also valid in a three-dimensional problem in most cases, all right? In most cases, it's true. For higher energy levels, the damping factor of the wave function becomes less prominent, and your wave function enters more in some prohibited region, say. Okay, so the higher the energy of the bound state, the more extended is the, the wave function, and the more likely to find the electron outside the box. All right, this is it. Well, if you plug in some values, I'll let you with exercises, but for some values here, for U naught equal to 3 electron volts, all right, if you plug in U naught, U0 equal to 3 electron volts, and D equals to 1 nanometer, 10 to the minus 9 meters, so 1 nanometer, all right, you'll find out. Then the mass, consider the mass of an electron, a free electron. Okay, if you do that, you will find three solutions, which corresponds approximately to E1 equals to 0.3 electron volts, some E2 equal to 1.19 electron volts approximately, and E3 equal to something like 2.58 electron volts. You'll find out three solutions using these values for your problem. Okay, try to find out, try to solve for D equals to 2 nanometers, U naught equal to 3 electron volts. Keep the mass of the electron in first case. Second scenario, D equals to 1 nanometer, U naught equal to 6 electron volts. So you're doubling the size of the box in the first problem, and in the second problem you are doubling the height of the barrier, right? And also you can mix things. Third case, suppose 2 nanometers, U naught 6 electron volts. All right, you can solve an equation of that type and find out what happens. All right, but now let us remember the wave function in the region 1 as a function of x corresponds to some value which must be determined by the integration from 0 to infinity, because from minus infinity to 0 the wave function is 0, of modulus squared psi of x dx equal to 1. So there are two main regions from 0 to d. You'll have psi 1 of x modulus squared plus an integral from d to infinity modulus squared of the psi 2 of x dx, and this sum of integrals must be unity, must be 1, because of the probability of finding the particle must be 1, all right? So in region 1, this is the solution, and in region 2, this is the solution, some b value exponential of minus I'll write some b prime here. Exponential of minus alpha x minus d here. These are the solutions. And you must remember that b prime is equal to a, so there are only one constant to be determined from this equation here. So it's a sine of k times d. All right, this is what you need to find out. This is an exact analytical solution for your problem. But of course, the main problem is to solve that transcendental equation for the eigenvalues. All right. Well, now you can see what it would looks like your solution. All right. If the potential is this thing here from 0 to d, right? You have a set of solutions here. So some E1, some E2. For one dimension, the distances increase. So you have some E2, some E3 solution. All right, will be a set of solutions. And if you pick the first solution here, you'll find out some function which is a sine, and here it will decrease. All right, this is the, if you sine here, and it will decrease exponentially outside the box. Notice that there is a probability of finding the particle outside the box. This is the box, here is the box. There is a probability of finding the particle outside the box. The second level, modulus squared, so the function I'm plotting here, perhaps exaggerating for the first level here, psi squared. So in this region is a squared, sine squared. In the second region is b prime squared, exponential of twice that alpha value. If you go to the second level, so this is the psi of the first level squared, the second level squared function, you have something like this. And it goes farther apart from the box. All right. And there are two peaks which corresponds to one node here, just one node. First solution inside the box, no nodes at all. The second solution, it will have one node. If you plot not the squared value, but the wave function per se, you'll find out something like this. Negative values. All right. My graph here, my plot is not perfect. All right. Third solution, you'll find something like one peak, another peak, another peak, and then it goes further, and you'll find one, two nodes. So for the nth level, you'll find out n minus one nodes. All right, this is a feature. This is a feature of the solutions of this quantum mechanical problem. All right, and the higher the energy level is, the larger is the probability of finding the particle outside the box. Near the top of your potential well of your box, near the top for energies near here, this function becomes very extended in a prohibited region, prohibited from a classical perspective, because for energies lower than u naught, you would have here a purely imaginary velocity for the particle, which is not possible classically. All right. can solve problems. Also, you can estimate what is the number of bounded solutions. You can estimate the numbers. All right. So remember that alpha corresponds to this function here for bounded states. Okay, for bounded states. And for the very low states, the lower states in the box, which means bounded states, the top of your well seems for a particle living down there as infinite. So you can think that the energy levels for the lower levels corresponds to approximately to the levels of an infinite square well, which are h bar squared, pi squared divided by twice the mass, the size of the well squared, some integer where n 1, 2, 3, and all that. But for infinite well, you'll have an infinite number of solutions. For the case of finite well, you'll find out a finite number of solutions. And we are trying to estimate how many solutions. So how many bound states? Well, let us plug in some approximate eigenvalue, which corresponds to the infinite well. In this case, we know that it is not an infinite well, but for lower bound states, it is a very good approximation. It varies for the higher energy levels, but it's not so far apart from that energy levels. And in this case, remember that alpha in the limit is zero. Otherwise, if the energy is greater than u naught, you start to have values of alpha which are purely imaginary, so you don't want that. You want bounded states, energy is lower than u naught. In the limit, the energy is equal to u naught, and you find alpha going to zero, which corresponds to u naught to be zero here. You can forget the mass, this factor, this h bar here. This must be equal to that in the limit. Okay, so it's just a rough estimate. Okay, in this case, you find out that the energies, of course, the energies must be lower than u naught to be bound states. And in this case, if you plug in that equation, u naught must be lower than h bar, or at least approximately h bar squared, pi squared, n squared divided by twice mass, d squared. And in this case, you'll find out your maximum n, considering, of course, an approximate value for the energies inside the box, but you'll find out that n will be in the range of it's an integer value. If you calculate this way, you'll find out a real number, but you can round, and the solution will be one more, or round up or round to the lower integer from the value you calculate here, but it's in this range here. Twice n d squared divided by h bar squared pi squared. You need to multiply by the u naught. So this factor here, this factor divides. You will find out n squared. You need to take the square root of this value here. This is the number of solutions you have for bound states. You need to round up their number, okay? Probably you find out something like 2.9, so you have likely three bound states. Or perhaps in another problem you find out 3.1, 3.1. So most likely you find out three states. So this number will not be integer, but you need to just round to the next integer, or the integer in the vicinity of that, in the neighborhood of that value. All right. For the problem or the problems, you can find problems I stated for you to calculate. You can find an approximate number of bound states, calculating this, and you calculate the eigenvalue problem, you find out it works pretty fine, right? So we can roughly estimate the number of values inside the box, of states inside the box. If you calculate numerically, just discretizing the Hamiltonian, you need to set your x vector from 0 to some 4 times this size of your well, all right? If you plug in 10 times here, okay, better, okay? It's a better solution. But perhaps you need to consider too many points, which will turn your algorithm not so fast to solve an eigenvalue problem, right? But modern computers can do the math for you. So try it with a number around 500 points, right? It will work just fine for this problem here. All right, next, let us try to discuss another interesting issue here, which corresponds to some problem like that. Suppose the following. Suppose you have in the x-axis two distant wells with size equal to d. All right, and apart, if you consider the centers, some distance L or R. Let us use R. Okay. Suppose this is your problem. Okay. Two asymmetric wells. They are apart by a large distance. For start, suppose this is going to infinity in the first step. And you know your solutions have the following form here. You have a finite number of solutions in each well. Besides being, if you put a mirror here, besides being the reflection, one side is the reflection of the other, besides that, the solutions have the same behavior. So the first solution is something like this. For the first well here, it's something like this, and this which is goes rapidly fast to zero, so it doesn't see the other potential well. And the solution here is like this, all right? The same. It's the same. My plot here is not so good, but suppose they are the same solutions. And at first, these two wells, these two boxes, do not see each other. They are apart a very large distance, all right? And then you have a set of solutions here. So you could enumerate the solutions here. So you have a solution one with an eigenvalue n equals to 1. The solution of the second, so these two, this number here is just to label the second box, n equals to 1. Here you have for the box number 1 a second energy level. For the box number 2 you have a second energy level, and they are exactly the same because they are further apart, very large distance apart from each other, and the energy levels are exactly the same. So you have corresponding to this some energy E1, so energy E2, energy E1, energy E2. Of course, you can use different boxes, all right? You can use D1 and D2 here. So they are just like in one dimension, two distinct species, two distinct pseudo atoms. But here I will call boxes. These two boxes are, it can be different from each other, but I am considering the most, perhaps the most interesting case, which is they are equal. And at, at the beginning, they don't see each other, so the energy levels are the same. The shape of the wave functions are exactly the same, just that to get that function of the second box, you just need to pick box 1. So if you have the function of the box 1, level 1 as a function of x, how can you find out the function for box 2? Okay, this is just a reflection. So if you symmetrize, you can just translate all the problem. So this R is divided. Suppose now I put 0 for the x-axis exactly in the middle of these two boxes. So the previous functions which we already found, I need to translate R over 2 to the left. All right, so the previous solution is located by R over 2. And the other solution, what is it? It is just the same solution dislocated to the right, but you need to reverse the regions. All right. So I'll just say minus x plus r over 2. Right. You need to reverse. You need to reverse the regions. All right. But I'll formally say this is just the same as the function 1 for the first level, but dislocated, mirror reflected. All right, this is it. This is this is the wave function of region 2. It's the same orbital. Say it's the same orbital. It's just reflected, and dislocated, displaced by some amount. Okay, so your original problem was this one here. All right, this is x, this is d, and it starts from 0. Now if you just translate it by an amount of r over 2, all the problems, you have the same orbitals, but displaced by some value, all right? So you have these things here. You have, say, a complete set of functions. Usually, the higher energy levels overlap more because alphas are lower and the electrons or whatever the particle is enters more into the prohibited region, classically speaking. But let's suppose here the only level occupied in our problem is the first level, all right? There is only one particle at the fundamental level of the problem. Now you are trying to use basis, a particle which can be in the box number 1 at the first level, or a particle at the box number 2 at the first level, which we will call just 1 and 2. All right? This projected to this thing projected to the basis of position will look like something like this. All right? So 0 here, this is the box. It will look like this. All right? And the function psi 2 of x, the box is reversed. All right? The box is reversed. And this function looks like this. All right? This is what we are trying to use here. So the potential is infinite here. The potential is infinite here. The functions are exactly the same. Put a mirror here, you convert this into that, and this into that, all right? Mirror symmetry here, all right? So this is the wave function in box 2. This is wave function in box 1. Of course, you can consider higher levels. So for higher levels, this would be the solution of a second level. This would be the solution of a, sorry, this will be the solution of a second level. Mirror reflected levels, okay? That's it. Now your Hamiltonian is the following. H is equal to minus, represented in the position basis, all right? This is the Hamiltonian. You have the kinetic term plus the potential, which is now the superposition of both potentials here, which will correspond to the following problem. Right? This is a double well. If you put the particle in this well here, and if this region here is small enough, this is D, this is D, and this, say, is some C, right? If this C is small enough, this wave function becomes more extended and it will see the other box. And in the other box, there are no potential for evanescent waves and will become, again, a propagating wave. So it will connect to the other state. All right? This is very similar to some problems in optics. All right? But what happens here? If you put a particle inside this box, it can see the other box and it can tunnel to the other side. It can pass through the barrier here, and the particle initially here will go through the barrier and will be found at a later time in the other box. So this is box 1, this is box 2. So how can we calculate the eigenvalues, the eigenvectors, and all that of this problem? All right? How can we do that? How can we do that calculations? All right? Well, we just suppose, because these wave functions are not exactly orthogonal, okay? So you need to find out an orthogonalization procedure. For instance, Schur's orthogonalization, okay, to be precise. You can pick up these functions, function 1 and function 2, and rewrite it as an orthogonal basis 1 primed and 2 primed, all right? You could find that. But suppose, and it remains valid mainly for the lower states in the boxes, all right? It is really a good approximation. Suppose the functions 1 and 2 are orthogonal. So they form a complete basis, all right? So basis 1 and 2. This is a two-level problem. Now, we have two potential wells, a particle which can be in either of the wells, and the particle can tunnel from one box to the other, passing through the barrier. It has energy lower than the barrier, but it can tunnel because it sees the other barrier. And we are considering as the starting point for solving the problem, as a starting point, we are considering the solutions of the problem of a single well. All right, the single well is the basis, right? But is just that the function 1 and the function 2 are or can be connected by mirror reflection and translation. It's just what you need to do. If you have the solution of one well to find out the solution for the other well, you need just to reflect the solution and translate and displace the solution. That's all you need, all right? So suppose this point here in the middle is minus r over 2, and this point here is r over 2, so you can calculate this limit and this limit, all right, you can perform the calculations. But now use this as a basis. So 1 projected into itself, it's already normalized. Also, the function of the second well is already normalized, but they are supposed to be nearly orthogonal. They are not exactly orthogonal, but you can orthogonalize by a proper procedure, which is called the Schur orthogonalization. You can do that. But as a matter of fact, these functions are nearly orthogonal. They are nearly orthogonal as a first approximation. All right? This way, you can have the completeness. It's a 2 by 2 identity matrix. All right? They form a complete basis. You are using this orbital, I will call it orbital, this orbital, and the second orbital is the same as the first, but just dislocated or translated and mirror reflected. All right, this is what you found. And now you can represent the Hamiltonian in this basis. All right. So what you have a Hamiltonian which corresponds to 1, a Hamiltonian represented, This is the single particle. I'll call it H1. H1. Right? This is the representation of this Hamiltonian, and just it is just a two-level system. All right? If you consider only one orbital coming from each box, and particle can be, if boxes are really distant in one and in the other, they are orthogonal states in this case. But if you bring them back together close enough, the particle can tunnel through the barrier, and these non-diagonal terms of the Hamiltonian will become tunneling probabilities. They are related to tunneling probabilities, and in this case, you'll have something like this. Some H which is equal to E1 if you're considering just the first level. It can be there can be a small correction here, right? E1 prime, but it's nearly E1, nearly E1, and you will have a delta and delta complex conjugated here. This is a two-level system, all right? So how can you perform these calculations to find out the elements of your Hamiltonian? Well, if you want to calculate one projected into that Hamiltonian with two, you just insert the identity here in the position basis. You can insert it here. But just remember that this Hamiltonian is already in the basis of position, so you need just one of the identities here in this case. All right, in this case, you can do that. And you'll find out that this is the integral over dx, because you are projecting to the basis of position, the integral over the x of 1, h, x, x, 2. This is the Hamiltonian represented in the position of, in the basis position. You can integrate from minus infinity to infinity, because in the regions where the functions are zero, just will be removed out from the integral. There's no problem with that. So this you'll find out here, because of the Hamiltonian operating on x is just representation of the operator. You'll find out the psi1 complex conjugated depending on x, which is the function, something like this, all right? The function in the first box times minus h squared divided by twice the mass, second order derivative is kinetic operator, plus the potential energy, which is that profile. This is the u profile. This is this function here. It looks like this. And in another problem, it will look like whatever it is, all right? And this is just the function psi2. And notice an overlap is needed, because if the function psi1 is 0 in some region where psi2 is maximum, it doesn't matter. The integral becomes 0. The integral becomes 0. So, as a matter of fact, the integral is relevant here. Why is that? Because too far from the box number 1, the psi1 function is already 0. All right? And too far from the box number 2, so this is 1 and this is 2, the wave function on the box 2 will be nearly 0. So the products here, considering, you need to consider operator, but in this region where the potential is the barrier potential, in this region the overlap is maximized. So as a matter of fact, not only you can perform exact calculations here, but in this region, the barrier region, is where the wave functions overlap the most because they are small, both are small, but non-zero. Here, function 2 is 0, and there, function 1 is 0. Here, neither of them are 0. So here in this region, inside the barrier, the functions will be maximized. And this way, you are calculating by this integral the delta in the two-level problem, because you are expanding the Hamiltonian of your problem, considering a well-known basis from a previous problem. And this because you are just neglecting some factors. For instance, if you consider the integral only in this region, you are doing some kind of perturbation theory, all right? And well, but the problem, which is corresponding to some number of bound states here, will be if you are just considering the first level or the second level or the third level, if you're considering just one level from each box, coming from each box, your problem is just a 2 by 2 problem. It's a two-level problem. You just reduced your problem in the context of a 2 by 2 matrix. All right. And this you can promptly diagonalize. You can promptly solve for the eigenvalues. And in this case, you'll find out that some state which will be the symmetric state because it's the sum of the two eigenfunctions, which increases the probability of finding something between the two boxes. The probability here is increased. It corresponds to a constructive interference of the two wave functions. The symmetric state will be 1 over square root of 2. A probability in equal proportions because both wells are exactly equal, of the particle being at this box and the particle being at this box. And the anti-symmetric state corresponds to the higher energy level, which is just this state here with a minus. This is a destructive interference. So the probability of finding the particle in the intermediate region here in the middle of the two boxes will be vanishingly small. All right. So this increases the probability of finding the particle here because you are adding up these two functions, and the anti-symmetric, the probability in the middle is decreased to 0. All right. You can find out it's a very very typical problem in quantum mechanics. And also you can, since you have these states, you can calculate the tunneling. How can you calculate tunneling? Well, you have the states, you'll calculate the energies. So for the symmetric states, the symmetric will have some energy nearly equals to E1 plus some delta in modulus minus. Sorry, this is the lower level. And the anti-symmetric, it will correspond to the same energy plus some delta. And you can just look at this, the one state. If you put the particle in the box number 1, it is the same as adding up these two states. In this way, you can calculate the evolution of this one over time, right? This state evolving accordingly to time, which is just the full Hamiltonian times t divided by the h bar times this state at 0 time, and you'll find out something like the spin precession, but here is the flipping of spin here. In the precession, you start with spin, the magnetic field in some z direction, and the state in the x direction. You'll find out that the spin rotates, and at some point it will reverse the sign, and then you rotate again, and it keeps rotating. This is spin precession. In this problem, you'll find out that this state here, which is putting the particle in the left box, the particle is initially here, it will tunnel to the second box. There will be an instant of time that the probability of finding the particle in the second box is maximized, and then the particle reverses and come back to the box number 1. So this is 1, this is 2, and then it goes back to number 2, and it keeps tunneling forever here if the problem is uh, non-perturbed by any other means. Right? So the particle starts here, tunnel to the right hand side, and after being here, it will tunnel back, and it keeps tunneling from one side to the other. All right? It's just because you can calculate the probabilities of giving this. What is the probability of finding the particle in the second? So what is the probability of finding the particle in the second box if you initially put the particle in the box number 1, but it evolves in time? All right, so you can calculate that. This is a summation of symmetric and anti-symmetric states, which corresponds to something like this. And you can perform the calculations. All right, but it's a very interesting problem. It has to do with tunneling, and I will let you to do the calculations, to do the math. It's a very, very interesting problem. It is related to a very simplified and oversimplified, perhaps, version of the Maser effect, but is a molecule which has two configuration states. So this is a potential distribution for configuration states. It's a variable here, which is not necessarily x direction, but you have some, the ideas are very similar. You have two configurations, and the molecule can be here or in the other side, but you can perturb the system and it will tunnel from one to the other energy. You can eventually, by perturbation with electric fields, unbalance the boxes or the two regions of the potential. But so far so good. I'll finish it here. Please do the calculations, do the math. Just try to implement it numerically. Try to figure out by yourself what is happening here. If you understand this kind of problem in quantum mechanics, you can do a lot of things. So see you next time. Bye bye.